I'm Stephen Foskett, organizer of the Tech Field Day events, and what you're about to watch here is a presentation where Rubrik is going to be presenting to a panel of delegates from around the world. These folks specialize in enterprise IT technology, and they're here to ask questions and discuss and learn about the technology. If you're interested in learning more about this event, you can find out by going to techfieldday.com. And if you enjoyed this video, you can find a lot more at youtube.com/techfieldday, or just use the Google.
Okay, cool. So first, just a little background. So I'm Adam. I'm the team lead of Atlas. It's our distributed file system. I came from Google. I did 9 years there, working primarily on a system called Colossus, which is Google's file system. So almost all data that lands on a disk at Google goes through Colossus and is managed by it. So I was really excited to come to Rubrik and build the same sort of web scale infrastructure for enterprise.
Hey guys, second time here, Rolland Miller. I was actually with Bipple the first time we announced Rubrik at Tech Field Day. My background is basically 17 years storage and backup systems. I cut my teeth on Networker back in the late 90s when I worked at SGI, back in support. So unfortunately, I'm sort of the industry veteran. I've sort of seen all of the progressions of all these products along the line. But what I'll talk about on our session is really just what I saw, the potential in the platform that really excited me. And a big part of it is what Adam's going to go into is the file system is really kind of a reset building on top of a new platform.
Okay, cool. Oh, and that's Charlie. She's my dog.
Security.
Just thought that picture was really cute. So, yeah, so we're really excited to present what the team has built to you guys. Let's see. So, quick agenda slide. So first, what is Atlas? It's our distributed file system, but just sort of introduce some sort of key principles. Scalability. That's really important that it can scale. So, how do we do that? What are the architectural decisions we made? Fault tolerance. What are the failure tolerance properties of the system? Application awareness. So from the get-go, the file system was built with our application in mind, and so we'll go into some of the use cases and things we've done to make our application really effective. Another slide on performance, just some quick things of how we make things fast. And finally, deployment. How do we deploy the file system itself?
So the core fundamentals of our platform is our architecture, right? So one thing to understand about the platform, our session today, what Adam's going to talk about is Atlas, but just to see the overall architecture of how the platform is designed and built, is you have basically the foundation or the core of the system, right? So the file system itself is really the centerpiece of that. And then we have the applications that support it. So Callisto is our distributed metadata store. This is basically, if you think about traditional backup and recovery platforms, think of this as your catalog, your metadata store. So all of the metadata is kept here and is tightly coupled with our file system. And then cluster management, right? So how do I talk to all of the different components and manage all the resources within the clusters? And then the distributed task framework, right? So think about job scheduling and how in backup recovery you'd have a single job scheduler, and if that server went down that had that, well then no jobs could get done. For us, this is all about how do I build every piece of the software stack into a single component and then deploy that in a scale-out fashion. So this way that if a single, in a fault tolerance standpoint, if a single node is down, well guess what? Your jobs continue. The other applications, the other nodes will continue to work and operate and execute their code. And then that was the foundation of the platform for scale out. And then we built the applications for backup recovery, search, deduplication, and the higher level or the higher order applications above that, right? And then that became really the internals of the system. And then here's all the external interfaces for connecting out to the real world. So the user interface, right? So all of the REST APIs, making that an easily consumable platform. Which our own user interface uses, so our HTML5 web interface, the cloud connectors, right? So how do I export and bring data, take it out of the system and bring it into the public cloud or the private cloud and be able to take data that I have in my system, but also get it out as well. And then all of the ecosystem integration. And so this is where you get into the first part of that when we first built the platform was VMware, right? And it was because that was the largest market segment. That was the best part to start with. But now we're continuing to expand. And for us, it's really just about adding modules to what we call the infinity layer, so that as new applications come online, new types of data services, whether it's file systems or applications, right now it's just we have to build a module or component to talk to that application type. Then now we can ingest that data, manage it, process it, store it, and then also bring it back up and instantiate it back into your user space as well. So,
okay.
Now we're going to talk in depth around Atlas.
Right, so we'll focus on the file system now. And I forgot to mention, so the slides sort of stay at a high level, but if people have more detailed questions, please feel free to interject and be happy to answer.
You really did build it, by the way.
Cool. So yeah. So what is Atlas? So it's a distributed file system, right? So you start with nodes, right? They have compute and disk attached to them. The little square-looking one is supposed to be Flash. My PowerPoint skills aren't great, so. Though I did learn how to use animation, so if I went a little trigger happy during the presentation, that's my bad. So Atlas, runs on top of these nodes, right? And what it does is it assembles all these storage resources, disks and Flash, and makes them accessible to our application, right? So our application just sees a normal file system. They have no idea it's distributed or fault tolerant. They don't need to know how it works, right? They're just writing files. And that makes their life really easy. And this is how with this distributed fault tolerant scalable file system, we can build Rubrik to scale out as well. Oh, right. Oh, Chris Wall trolled my slides. I forgot. So yeah, it's like saying right. It's assimilating and becoming more powerful. It's like Borg, right? But no. It's actually like this nice guy who helps you store stuff. Okay, cool. So what are the properties of Atlas? So it's a distributed file system. It's homegrown, so we wrote it. And one of the important things about it is we can design it with our data management application in mind. And we'll talk more on later slides about how we make the data management life a little easier. So it's a global namespace. All the storage resources are distributed, but the application just sees a file system locally. The data is stored on disk or Flash. We'll talk about how that's controlled later. Metadata stored in our distributed metadata store. So Rolland mentioned that earlier. We call it Callisto. It's where we also store our catalog metadata for snapshot management. But the file system actually leverages that same system to store its metadata, so the file system metadata itself. The nodes communicate through RPC, just an acronym for remote procedure call. And we rely on the cluster management service called Forge to tell each Atlas instance what the cluster topology is. Okay, cool. So another picture with animation. So you start with a node. It has disks and Flash. Atlas starts running on it. It connects to those, or it knows about those disks and Flash, and will serve those to other nodes. Each node sort of looks the same, right? There's disks and Flash, and there's Atlas running there. Our application is running on some node, and it's just talking to the local Atlas.
Yeah, so each one of these really just becomes its own separate resource, right? And they're all fully independent of each other. And so you'll hear some concepts around like master lists that, and how all this ties together. But basically, each instance of Atlas owns its local copies of those disks and Flash resources. And then from there, they can all communicate and talk and then basically build the hive mind.
Right, so application writes to Atlas. Atlas just writes, might write to itself, and it might write remotely as well. And finally, our metadata is stored in the system called Callisto. Any questions so far?
So the metadata is actually, it's on each one of those nodes.
Yeah, so the file system itself treats the metadata service as a service, so it doesn't really know or care. It just assumes that its metadata is distributed and also fault tolerant. The truth is, the metadata service, yes, replicates to all nodes, or not all nodes, but replicates across nodes as well, so that if some node dies, right, you don't lose that metadata.
And the metadata also, the way Callisto operates is that it also tiers out the metadata. So as we get into things like, general search, there's a lot of that is still stored in Flash, but then we can take additional, like deeper indexes, like when we index files in the file system, then we can actually tier that down into the disk layer as well, which is distributed by the Atlas file system. So that way we can get very high performance lookup, but at the same time without exploding the namespace for the metadata, so I can be really efficient on how much flash is actually required to service all of the nodes in the platform.
And an exact copy of the metadata is also with the cloud if you archive out to...
That is correct. We actually will, when we archive out and push out to the cloud, we send the metadata with the data as well.
Right. So metadata is a bit overloaded in this context. So for the purpose of this talk, metadata will refer to just file system metadata. What Rolland and you are discussing is sort of the metadata for the snapshots itself. And we call that sort of Cerebro. That's the data management layer. And so there's a bunch of metadata associated with, like, what VMs are we protecting, what are the snapshots that we have, and all that's also metadata technically, but it's sort of at a level above the file system.
Sure, that makes sense.
Though it is actually still stored in Callisto.
This is the metadata.
Okay, cool. So scalability. Right, so scalability is a big thing if you want to build a big cluster, right? So one of the key decisions we made was to make it masterless. So all nodes are essentially peers. There's no single choke point, no single point of failure. This is actually a property of Colossus at Google, which is the second generation file system. The first one actually wasn't masterless, and Colossus was sort of born to address that problem. So we designed Atlas in the same way. So no single point of failure. Scale out. Each node is the same. Nodes can die. Other nodes can pick up the work on its behalf, and things just sort of go on, business as usual.
Does that concept make sense for everybody? I mean, any questions around that? Cool.
Okay. We'll have more pictures too, so maybe that will spark some questions. Cool. So yeah, we use cluster management. Just publishes a list of nodes that are participating in the cluster, and Atlas uses that list, as to discover who it can write to, who it can read from, and it's actually topology aware. So we'll know like which nodes run which brick, and it's extensible. So you can imagine cluster management telling us sort of the topology of the cluster and trying to spread replicas as wide as possible to increase fault tolerance. Like I just mentioned on the last slide, so the metadata is also stored in a distributed fault tolerance system. Wouldn't make sense to sort of distribute and be fault tolerant at the file system layer if your metadata for that file system doesn't have the same properties. And the maintenance is sharded. So it's a self-healing system, which means there's work to be done to manage the data that's stored within it. And that work is spread amongst all the nodes participating in the cluster and divvied up equally amongst them. Cool. Okay, so we're on to the picture. So so this is like the story when you have one brick with 4 nodes. The 4 of them form a cluster. You have this metadata service running. Then you add another brick. Okay, so what happens, right? Those nodes just appear, those nodes just appear to Atlas from the cluster management system, and it starts making use of them. And this is your scale up picture, right? Just keep adding more bricks. It adds more nodes. Still one cluster. So same global namespace. You just added the capacity of the new nodes.
So that was kind of going back to the first slide where he had the command line and he showed the the capacity. You do a ls and see how much capacity is in the file system. As you start there, you add goes 50 terabytes. You add the next one. Now it's 100 terabytes. The next one. Now it's 150. It just continues to scale out. Basically until you run out of rack space and power. So.
Now I'm assuming, like if you add nodes, it's going to rebalance, but that's not necessarily part of the Atlas file system that's doing that?
Actually, so Atlas does manage the data placement, so we will rebalance. Though it's a background activity, so it's not like you drop a brick in, all of a sudden your cluster goes crazy. Right? There's throttling and sort of smarts around like how to rebalance, when to rebalance, based on what the cluster topology looks like and sort of what's going on in the cluster.
Okay.
Good question. Okay, so fault tolerance. Of course, we're built on commodity hardware. Things fail. Right? We need to make sure we don't lose data. So what do? We replicate. So our fault tolerance properties are 2 disks or 1 node. So any 2 random disks in the system can go away, and we should not have lost any data. Same thing with a single node, which will knock out 3 disks, but we take care to not place too many replicas on any one node. Okay, so how do you do that? You use a replication strategy. So pre 3.0, we use something called mirroring, and there's a follow-on slide just to sort of demonstrate that. But in post 3.0, we've made erasure coding the default. And there's another slide to sort of go into how erasure coding works.
the key benefits of switching from the triple mirroring to the erasure coding was we wanted to be able to provide the same level of high availability that we got with triple replicating the data. But unfortunately, the capacity of that, that's the other side of that coin, right? Is the penalty for capacity. Erasure coding and the design we went with erasure coding is going to allow us to provide the same level of high availability, but double the effective capacity of the platform, all through software.
How come for the first version you used mirroring at all then? Was it just for simplicity's sake to get it up and running?
Essentially, yeah, mirroring's like pretty easy to reason about, right? Any piece of data, I replicate it, I can read from the other one, as if it's an exact copy, because it is. It just gets a little more. Story gets a little more complicated when you have erasure coding. We can dive into that too maybe on the erasure coding slide.
Is that upgrade non-disruptive, or do you need any downtime to?
So the upgrade is not disruptive. It's just the default policy for new data creation. So as new snapshots are taken, all that data would be written in Reed-Solomon format. Furthermore, the system has a background process to sort of churn through it and modify things. So we've discussed whether we want to make that sort of the default thing to just transcode everything. Right now it doesn't. The system sort of will write you new data in erasure coded format as it's running, but we don't make a wholesale pass to go as soon as you upgrade to churn everything.
Yeah, typically, just because of the nature of the platform, the SLAs, and the way that new snapshots and backups are taken, and then they're eventually aged off. Most customers have very short policies, 30, maybe 60, 90 days at most. But then over that period of time, those older copies are going to get aged out, and the new snapshots are going to replace it. So all the new snapshots will come in as erasure-coded copies, and the old ones will simply expire and be garbage collected.
So customers are basically upgrading and getting more capacity, I guess, eventually.
Yeah, that's right.
That's right. And this is all built within the file system. So even our data management application, the thing that's dealing with snapshots, snapshot chains, and all this, has no idea that it's happened, which is kind of nice. So it doesn't have to think about it. It's just using the file system as it normally was. But all of a sudden, things are taking half as much space. So the system is self-healing. Anything written into the system is managed by the system. So we rely on cluster management to publish node health information, node and disk health information, and we'll react to that. So if we see a node fail, we'll re-replicate the data that was stored on that node. And I've got a great animation for you guys on that. Again, the placement is topology aware. So the file system is choosing where it wants to replicate the data to, and it knows a little bit about the cluster, right? Which nodes are on which bricks, and you can extend that to sort of which bricks are on which racks, which racks are in which data center. We don't have that ability yet, but certainly the way we built it, it's this generic framework, so it could be extended that way.
And the other thing I'll comment on that, though, is that as the system grows and you add more appliances, more bricks, that topology awareness really allows us to increase the availability as the system gets bigger as well.
Oh, and finally, one note. So we use CRCs for data integrity. We have CRCs all across the stack, but this is protect against things like cosmic bit flips. So randomly, one of my replicas goes bad for some stray beam in the universe. But we'll discover that and we'll throw it away and replicate that data. Okay, cool. So this is what the picture looks like with mirroring, right? So you have your file. Let's call this orange thing a chunk. We actually store 3 copies of this chunk spread across the system on different disks. So let's say a node on this third brick dies. The file system will notice it and just re-replicate to another disk somewhere. Now, in this picture, you can see there's actually 3 bricks, and because the file system is topology aware, we've actually placed those 3 replicas on different bricks. So, same thing holds when an entire brick dies, right? You actually haven't lost all 3 of your replicas. You still have 2 left, and you just do the same operation to move it, wherever you have space. And obviously, as the system grows, right, you have more and more choices of where you can put stuff. So you can increase your failure tolerance, as Rolland was. Does that make sense?
If you lost a whole node there, would you still copy one of those existing chunks to one of the 2 remaining bricks?
I mean, if you lost a whole
brick. Yeah, so for example, in this
you lost
scenario,
the whole brick.
right?
Yeah.
You lost the whole brick. Then the next operation after this is now it's lost its 3 bricks. So now it's going to have to force that copy. It'll send it to that another copy will exist on one of the other bricks. However, it'll still put it on, a different disk and a different node within the same.
Right. So the cluster is adaptive, right? So we value failure tolerance above like sort of spread across the topology. So we always try to replicate you fully because we don't want to be in the state where we're sitting with only 2 replicas left because we haven't sort of satisfied our failure tolerance guarantees. So we'll always try to create a new replica. The one exception is if you have exactly 1 node left, we won't put all 3 replicas on that 1 node.
Okay, and
That
if
would
you
violate our-
replace that brick eventually, will it then in the background move those blocks back over?
Yes, so as I said, the system is self-healing. It also runs background maintenance, and one of those operations is trying to increase the failure tolerance of existing, we call them stripes. So if I have a 2 brick setup and I install a 3rd brick, all of a sudden now I can tolerate a brick failure if I'm able to spread my data across all 3 bricks. And so the system will try to do that in the background.
Can you see the current progress of that rebuild going on if that happens, if the last entire brick?
So certainly in the UI, you would see that nodes are down, but you do not see at the level of the file system, what sort of replication or maintenance operations are going on. Certainly we have that information, for our internal stats and reporting. So potentially you could get to it, but right now it's not exposed in the UI.
Will the addition of that 3rd break immediately trigger the rebalance, or is it something that's got to wait for midnight for a job to kick off?
No, so there is no set schedule, but it is rate limited. So based on what is going on in the cluster, we'll sort of hold things back. We don't just start dumping everything we can as fast as we can to the new brick. And that's configurable from the file system point of view, but again, it's not like a knob you can turn in the UI or anything, though certainly we could think about doing something like that.
And sometimes, a failure like this isn't always, it's not like a failure of the hardware. It could just be network switch went down, these nodes went offline, but a minute later came back online, right? And before we've evacuated all the data, hey, guess what? This is here, and then we'll recognize that.
Or the guys blaming the network.
Yeah. Never happens.
Is it possible for you to, I guess, put an entire brick into maintenance mode? Like if you were going to take it offline and move it so that way it didn't try to rebuild on other nodes?
The answer to that question is yes. So we do have the notion of maintenance for a node. And when you put a node into maintenance, we will not recover the data that you've sort of made inaccessible because we expect it to come back. So it's treated differently than being sort of missing from the cluster. Right. However, in order to the file system has to greenlight maintenance operations, and what that means is we won't give you the go-ahead signal for pulling a node or pulling a brick until for any given piece of data there's at least one somewhere else. So you won't make any data inaccessible by performing your maintenance.
Is there a certain time period that after it's in maintenance mode and hasn't come back, it will trigger rebuild? Kind of like how PSAN does?
I don't believe that's true because we expect maintenance to be done, with an operator, like a human there, sort of babysitting it. Certainly something we could think about doing.
So you said that you have it rate limited for actually rebalancing. Is there any way that you can kill that rate limit for automatically? So imagine I want to put something in maintenance because I'm going to be doing maintenance on this thing. I have to take it down for whatever reason, and your processes haven't finished running. So now you won't let me take it out because it'll violate some data. I don't care about that. I just want to move this data as quickly as possible so I can take this thing offline.
Yeah, so certainly there are knobs, and we've thought about exposing a way to control how maintenance is scheduled. I mean, we do have sort of what we call him the maintenance man. He's the maintenance manager who's responsible for scheduling these maintenance. So when do I decide to recover? When do I decide to rebalance? How do I balance that against garbage collection? These sorts of things. So certainly we have the capabilities of tweaking the knobs, though we do not actually expose that right now.
This guy kind of gets into the area of design for user interface and simplicity and easy use, and it's about there's tons of nerd knobs under the covers,
right?
But right, how much of that do we want to expose? How much is it? Can you do through the APIs, and maybe so if you have to do it, things like this where you're talking about maintenance items, it's not like an everyday task
right.
That you're going to be managing, but it's definitely something that you can work with us in our support if we really need to get in there and do something because you have an exception. Our service support and engineering can help with that. But as far as a easy use and experience standpoint, we don't want to all of a sudden clutter the user interface with all of these buttons to go push and hope that you don't actually use them very often, right?
Yeah, to the vSAN comment, that's one of the things that I wish that it had, so that I could like eliminate any type of throttling that's going on, because I have maintenance. I have to do this right now to fit into my maintenance window. Flush all the data you can off of this node so that I can start using it or fixing it.
Yeah. So two comments on that. So first one is, for maintenance to be blocked, your last replica of a piece of data has to be on that node. So as soon as we've gotten one replica off of the thing you're trying to do maintenance on, you're sort of good to go, and you can go ahead. It's not like you need to drain the thing completely.
Yeah.
So that's one thing. And second thing is, we actually have a ClusterOps team which is working intimately with the file system to get feedback from the field on what sort of things are common operations, right? Like whether it's moving a node, plugging it in a different rack, or swapping a disk out or whatever. So we're sort of reacting to feedback we've seen from the field to see what actually are the problems that sort of operators have.
Yep. And then can you manually kick off a rebuild? Let's say your node's in maintenance, pull it out of the rack, drop it on the floor, light it on fire. I don't know. I mean, it's not coming back online. So is there a manual process, or is that a support call?
Yeah, I mean, sounds like a support call, though I don't fully understand your example.
Rubrik does not advocate setting them on fire.
Yeah.
Sounds like anger management.
Howard Marks isn't here.
Yeah.
They're mine.
Okay, cool. Any more questions on this? We can talk more, of course.
Great questions, thanks.
Okay, so a quick intro to Reed-Solomon, or Erasure Coding. So mirroring, this is what mirroring looks like, right? We have this orange thing, we call it a chunk, and we create 3 replicas of it and stick them on a disk somewhere. So Erasure Coding looks a little bit different. So you take, same piece of data, this time you chop it into 4, and we call those data chunks. From those 2 data chunks, you create 2 code chunks. And then, with this configuration for 2, you can still tolerate losing any 2 of the chunks and be able to reconstruct the original 4. I guess folks are familiar with Erasure Coding. It's not like a new thing, right? We didn't invent it, but cool. Okay. Okay. So application awareness. So the file system was designed with our application in mind, and what our application does is take backups. And the way it stores those backups are using these things called snapshot chains. So a snapshot chain is built from immutable point-in-time snapshots. And what the file system allows you to do is instantly materialize any one of those points in time. And because we know that they're related, we can actually co-locate their data to make things fast.
And it's important to understand the point of, immutable points in time is really about, the types of data that we're taking, the copies of the data. It has to be immutable, because you can't come back later and say, oh yeah, I was able to, through the system, modify that data, because, at least in the backup recovery space, hey, that data may be used in court somewhere, right? How do I know that this data was never modified, never changed? And so that was actually, a design point for the platform to make sure that people understand, hey, I can make modifications, I can make copies, but the original copy that I made, the hashes, the CRCs for it, they're immutable, right? Once I've taken that copy, this data, stays as a snapshot chunk within the system, but it's completely unchanged.
Okay, and then so certainly we have these immutable snapshot chains, but we still want you to be able to view a mutatable version of a snapshot. So we use something called redirect on write, and we'll have a slide to show how that works. And we also give our application control. So we know what our application is. We sort of listen to the things that they need, and then we give them control to modify various properties of the files they're working on. So for example, they can control the replication level of the file. If I'm creating some scratch file I know I'm going to use for 10 minutes and throw away, and I don't care if it dies in the middle, I can just rerun my job. You probably don't want to replicate it and spend the time to spread the data everywhere, CRC it and whatnot. Similarly, they control the media type. So do I want this file stored on flash or on disk? And also, there's some hints about placement. So the application can tell us, I want this file replicated on these nodes or near these nodes, and we'll do our best to accommodate that. And then because we wrote our own file system, we can provide the application these second-order features that you wouldn't get with some off-the-shelf thing. For example, or just a few examples, TTL files. So some application wants to create a file, doesn't want to have to worry about cleaning it up. They can create these special TTL files, which is cleaned up by the system on its own. Similarly, cancellation is just a way to sort of make a file not writable anymore, which can sort of cancel a process that's trying to write to it. So smaller things which just make our application's life easier.
The only thing I was going to say there is that that part there, the second order, is what really allows is the tight coupling between the higher level, the Cerebro, the data management applications, and the underlying file system. Because by having that communication between the file system and the application, right, we can do a lot of really unique things and leverage the resources and the resource pools below us, to have, to increase the performance, to be able to set the time to live and say, hey, I'm going to create this data. It's like scratch data, but I don't want to have to send another command to go clean it up. So I'm going to use it for about an hour. After an hour, right, let it phase out and be deleted as part of the garbage collect platform, right? So it's an interesting, use case, but maybe it's a little too deep, but it's something that I found that really tightly couples the higher level application, data management and data protection with the underlying file system.
Okay, cool. Another animation just to sort of demonstrate how these snapshot chains work. So this is probably a familiar picture for most folks. So you time zero, take a full backup, right? You have the whole entirety of the data. From then on, you're just taking incremental backups. So here, these yellow blocks are just the delta blocks at time 1 since time 0. This sort of goes on through time, right? You're taking more snapshots, just pulling in the delta blocks. But now, I want to actually use the snapshot at time 3 to do an export or restore. So what do? I actually just materialize, a virtual file that represents the content of the entire VM or VMDK at time 3. And the same for VMs and file sets and SQL databases as well. But we'll use the VM use case here. So I've materialized a snapshot at time 3. And that operation is just a metadata operation. There's no data movement. It's just pointers back to when was that block last mutated. Any questions on this picture? Cool. Okay, so let's say now I actually want to live mount this VM and do some mutations on it. So same thing, right? We materialize this immutable snapshot chain, but any mutations now come to a log file, right? So we just use this journaling system to sort of soak up the mutations, but we're not actually modifying any of the content, from the initial snapshots.
Right, and to extend on that, so as so that guarantees that any one of these point in times is fully materialized. It's immutable. Right, so that I'm not making any changes to the original source data, but as I make new changes and I'm writing out, new snapshots, and if at some, for additional use cases, things like copy data management, if I want to spin up a clone of this, well, then I can simply just protect this, and then it'll create its own immutable snap chain, a new chain that starts off of that base point, right? So I can take a snapshot that I've already mounted and back it up again, and now it has its own data protection policies.
Cool. So performance, just a few things here, right? So we have Flash. Flash is faster than disk. So the application is smart enough to tell us when the file's performance critical, and we'll actually put that on Flash on its behalf. Any unused capacity on the Flash device we'll soak up and use behind a cache into which we put hot blocks. So that way we're getting sort of good utilization of our Flash I/O. Furthermore, not all I/O streams are created equal in our world, right? We'd much rather prioritize, an ingest, of a VM that's held up in a VMware snapshot than some background, maintenance job consolidating stuff or that sort of operation. And finally, there's some awareness of the data locality. So we do our best to place related data close to other related data so that performance can be fast. Okay, final slide, I think. So deployment, it's a single binary, which makes it really easy to deploy and upgrade, et cetera. There's no, different server components, right? It's just a single binary, which is the client and the metadata management and the maintenance.
Yeah, I think, and this gets back to the point I started in the beginning where we talk about, it's a single software stack across all the nodes in the cluster. Because oftentimes, different software services have to be installed on different application servers, and this creates the complexity, right? The Erector set of backup recovery, where you have this application and server that you install this piece of software on, but this other server runs this other background service, and so you have to install these other pieces and components of software. For us, it's the single binary allows us to deploy the same software and apply it equally across all the nodes in the cluster.
And we leverage our core services, right? So the file system uses the same metadata store the catalog is stored in the data management application stores its metadata in. No reason not to use it. It's distributed, fault tolerant, et cetera. And cluster management. We use cluster management. The file system didn't have to build its own sort of node participation or cluster participation mapping. We just rely on the cluster management service to sort of see everyone who's there, publish their status. When something dies, let us know, and we'll take action accordingly. Cool. Yeah, I just wanted a quick shout out to the team. Great job, guys. Awesome stuff you built. So.